So this is where our story of the quantum begins. Max Planck, a German physicist, studied the blackbody radiation, and in order to resolve this ultraviolet catastrophe, he found that he needed to make a radical assumption, a hypothesis, and that is he had to assume that the energy of the electromagnetic radiation is not continuous. That is, it cannot assume any continuous value. It must be a set of discrete values. The energy of the electromagnetic wave must be a set of discrete values. HF, F being the frequency, 2HF, 3HF, and so on and so forth. And so basically it's NHF. N being a constant, 1, 2, 3, and so on. In other words, the energy of the electromagnetic wave radiation is quantized. I can draw the allowed values of the electromagnetic energy. This is HF, this is 2HF, this is 3HF, and so on. There is a gap between neighboring values of possible energies. This gap is HF. What is F? What is H? H is a constant which Planck discovered in order to match the theoretical calculation with the experimental blackbody radiation curve. And he found in order to achieve that match, H can assume only a certain value, and it is extremely small. Let me write it down for you. H equals 6.626 times 10 to the negative 34 joule Kelvin. Well, in fact, it's joule second, because that's how you cancel the units of frequency, which is 1 over second, to get energy of joule. I have never seen any other fundamental constants in the SI system with such a small value, negative 34. This is one of the most important fundamental constants of nature. We already learned a few of them. We learned G, which is the gravitational constant. We learned the Boltzmann constant K, and we also learned, of course, the speed of light. The speed of light appears in every formula that has to do with relativity, and the Planck's constant, as this H is known, is apparent. It appears in every single formula about quantum mechanics or about the microscopic world, the Planck's constant. We can sort of see why classical physics would fail at high frequency but not at low frequency. Because in classical physics, the energy of the electromagnetic radiation is not quantized. Quantization is something new. Now, we do not claim that we understood why it's quantized, but at least according to the hypothesis, it is quantized. And if we follow that hypothesis, we find that quantization is something new. And this quantization means that energy cannot be just any value. It has to jump from this value to the next, to the next. It cannot be anywhere in between. But the gap, look at the gap. The gap is H times F. And the greater the frequency, the higher the frequency, the greater this gap. Now, this gap did not exist in classical physics. So the greater this gap is, the more difference there is between classical and quantum physics. So the greater this gap is, the greater the difference between the predictions of classical and quantum physics. This explains why, with a higher frequency or a greater gap, you should expect greater difference. And this is why the Rayleigh-Jeans formula works quite well at low frequency when the gap is very small, so the quantization is negligibly small, and yet becomes prominent when the quantum mechanics cannot be ignored, which means the frequency gets really high. So the quantization becomes very prominent. So now let's see how the rescue effort comes underway, and that is, how do we use the newly assumed quantum hypothesis to resolve the crisis? Basically, when we calculate the classical expression, the Rayleigh-Jeans formula, we multiply two things together to get du, the energy between wavelengths lambda and lambda plus d lambda. And one is the number of oscillators operating between these two, between the frequency range or wavelength range, and the other one is the average energy per oscillator. And we cannot rewrite the number of oscillators between these two frequencies. That still holds true. But how do you calculate the average energy possessed by each of these oscillators? Well, classically, it turns out it has nothing to do with frequency. It is just k times t because of the equipartition theorem. But is it still true in quantum mechanics? Well, let's recalculate the average energy of an oscillator whose frequency is f. According to the quantum hypothesis by Planck, if an oscillator has a frequency f, then it must have energy of hf, 2hf, 3hf, and so on. So you can assume a whole set of different energies, and don't forget there is what's called the Boltzmann factor, which tells you, relatively speaking, what is the probability of a system assuming this much energy. So what is the probability of a particle assuming an energy of hf? Is proportional to e to the negative energy over kt. Energy is hf, so it's negative hf over kt. And it doesn't have to be 1 hf, it can be 2, 3, and so on. So in general, it's n hf over kt. N is a natural number, as you know. So therefore, what is the average energy of an oscillator whose frequency is f? Well, it's the sum of P energy and then times the energy itself, right? This is how we just average all energies using the probability. Now the probability itself is this, e to the negative nhf over kt, because energy is nhf, and then times the energy itself, which is nhf. You sum over n, that runs up all the possible energy values, n equals 1 to infinity. But I have to divide by something because the probability is not equal to this. We are missing a normalization factor. That normalization factor is 1 over the sum of all these Boltzmann terms, hf over kt. Okay, because when you add all the probabilities up, you're going to get 1 for all the possible values of n. So this is the average value of the energy. And we have 2 infinite series to sum up, but this is a very interesting exercise in math itself. You can see it for yourself, but just for the fun of it, let's do it together. First of all, you look at the difference between the numerator and denominator. The numerator for each term has an extra nhf. Denominator doesn't. In fact, I can get this nhf from here simply by bringing an nhf down from the shoulder of the exponential. How do you bring something down from the shoulder of a power function? Well, you take a differentiation. So what I do is, you remember beta is defined as 1 over kt in physics 1b. So we're going to restore that definition, beta here, just for the sake of clarification. And you can see here the sum. This is nhf e to the negative beta nhf. And you copy the numerator, negative beta nhf. Suppose I don't have this. How do I get this down from the shoulder? All I have to do is differentiate this exponential with respect to what? To beta, right? When you do so, you get a negative nhf coming down. So let's do that. Let's do partial beta of this expression without nhf. So it's e to the negative beta nhf. That's the numerator. The denominator, I'm just going to copy it for now. In fact, if you did that, you're going to get negative nhf. Now, there is no negative sign here, so I don't forget I have to attach a negative sign to cancel with that. And now we have the same numerator and denominator. If I sum one of them, I can sum the other. But before I even do the sum, you realize that if you call this function u, then you are doing basically partial u over partial beta and then divided by u itself. That is the same as partial beta of the natural log of this function. Right? So you don't have to separate the numerator denominator and do it separately. This is just that. Beta hf to the power n. And this n goes from 1 to infinity. Okay, when you do partial beta of natural log, you have to take the denominator first, divide it by, and then that's how you go from here to there. All we have to do now is to sum over this. beta HF, then it's to the power n. Now this whole thing here is a number. We call it x. And this x, as you know, is less than 1 because e to the power something negative. So it's less than 1. So really it's just a power function, x to the power n, and x is whose absolute value is less than 1 makes this sum convergent, and then we can easily apply a very well-known formula. The sum is equal to this. 1 divided by 1 minus x, right? N equals 1 to infinity. X to the power n is equal to this. Okay, let us finish this differentiation. And that's easy enough to do. You can flip the numerator denominator, cancel with that negative sign. Partial beta, natural log of 1 minus x. And then that is just 1 minus x. And then negative, you have to take it with respect to that, partial beta of x. X is given by this expression e to the power negative beta hf. So you do the derivative, hf comes down. So finally, you get this expression. One more step. You take the derivative, which gives e to the power negative beta hf, and then I multiply every term in the numerator and the denominator by the same factor, e to the positive beta hf, and so the numerator simply becomes hf, denominator e to the power hf over kt minus 1. I have restored beta equals 1 over kt. So let me box this incredibly important result. This is the quantum calculation for the average energy of a simple harmonic oscillator whose frequency is f. It is no longer a constant of kt, independent of frequency. It does depend on the frequency. It is hf divided by e to the power hf over kt minus 1. And h is the Planck constant, and f is its frequency. This is totally different from the classical expression. Now, with this new expression, can we resolve the Rayleigh-Jeans catastrophe crisis? So we're now going to have the so-called Planck formula to replace the Rayleigh-Jeans formula. Again, the energy inside the black body between the frequency f and f plus df is the product of its average energy per oscillator with frequency f times the number of oscillators. And this is the new expression for the average energy. And here is the old formula for the number of oscillators whose frequency is between f and f plus df. Now, the textbook doesn't want you to find per unit wavelengths. They want you to find per unit frequency. I'm sorry, the other way around. I have the frequency difference. Here they want d lambda in the textbook. But f and lambda are related, so we can easily convert. F equals c over lambda. The absolute value of df equals to, you differentiate that, c d lambda over lambda squared. You notice I add an absolute value because I don't want a negative sign here. It doesn't really mean anything here. So you plug that in, okay? You plug that in and replace f with c over lambda everywhere. You find that du over d lambda equals this. What is this again? This is the energy of the black body per unit wavelengths. That's for a black body of volume V. You can divide that V over, you take the total energy divided by V, you get energy per unit volume. That's called energy density. We use lowercase u to denote that. This is different from the Rayleigh-Jeans formula. So let us find the radiation intensity I in the quantum mechanical case to see whether we can recover all the correct results, such as the Stefan Boltzmann law and Wien's displacement law, and resolve the Rayleigh-Jeans crisis. One thing we have to be careful about is that if you look at different textbooks, different literatures, there are actually two different versions of what's called Planck formula. One of them is derived right here. That is the amount of energy inside the black body per wavelength difference or per frequency difference, which is right here. But this is not the same as the Planck formula you saw in our textbook. The one in our textbook is dp over d lambda, not du over d lambda. What's p? P is the amount of energy radiated out of the surface of the black body per unit wavelengths. So they're not the same thing. We are going to start from here, which already derived, to find dp over d lambda, which is the formula in the textbook. And they actually differ by a factor, which is a little subtle here. We're going to find it out. So let's see. How do we go from U to I? U is the energy density inside the black body, and I is the amount of power radiated from the surface of the black body. You know, photons move in random directions. Suppose this is a certain part of the surface area of the black box, of the black body, and we're looking at this little patch of area A here. The photons will make their way out of it through radiation, but depending on the direction and motion of the photon, it may or may not easily find its way out. If a photon moves parallel to the surface, for example, it can never make its way out. But if a photon moves perpendicularly to the surface, then even if it's pretty far away, it can still make it through the surface over a short time period because it's aiming directly at it, right? So suppose I choose a coordinate system. I call this the z-axis. And a photon comes in like this at an angle theta. What I want to know is, over a time interval dt, how many photons moving this way can make their way out through this surface so it can radiate outwards, contributing to the power of radiation. Well, these photons cannot be too far because they can only move a distance of c times delta t, c times dt over a time t. So they cannot be that far from here. They must all be within a certain cylindrical region, and this cylinder has a side length of c dt because the photons travel at speed c. It's got a bottom area of A. How many photons are there within this? If the number of photons per unit volume is n, small n, then if I take that n multiplied by the volume of this cylinder, then I will get a total number of photons, right? Total number of photons. Now, you take that n multiplied by c dt times cosine theta, and then times the bottom area A. This is the volume of the cylinder. Again, multiply the number of photons within that cylinder per unit volume, you get the total number of photons within that cylinder. All these photons will make their way out over time dt through this surface area A. Okay, photons move in random directions, so theta can change continuously. And theta is not the only angle describing the direction and motion of the photon. There is also another angle phi. This is theta, the angle made with the z-axis, and phi goes around the z-axis like that. Remember the spherical coordinate? And because of the random nature of the motion of the photon, we have to do some averaging here. So after the averaging, the number of particles dn, number of photons that can make their way out of this box, I have to average over theta and phi. Okay, so I take this function, n c dt a cosine theta. I have to average over all the possible orientations. And to do so, we have to use the so-called solid angle d omega. And we have to integrate. Then we divide it by 1 over 4 pi, by 4 pi, because 4 pi is the total solid angle for the entire sphere. So basically, we're averaging the orientations for theta and phi. In fact, if you recall, d omega is sine theta, d theta d phi. Then you have to integrate over theta and phi. Phi goes from 0 to 2 pi. And this theta here, be careful. Theta can only go from 0 to 90 degrees, right? Here is 0 degrees, and here is 90 degrees. You cannot go like that, because you go like that, if a particle goes like that, it will never make its way out. So we do this integration, n c dt a over 4 pi, from 0 to 2 pi d phi. That is for the angle phi, and it doesn't really matter. There's no phi dependency here. And then from 0 to pi over 2 cosine theta, and there is a sine theta here, d theta. This integral equals 1/2. This equals 2 pi, so you do this algebra, you find dn to be equal to 1/4 Na C dt. This is the total number of photons that can make their way out over a cross-section area d of A on the surface of the black body over a time interval dt. Now, if I know the average energy of these photons, which I call epsilon bar, okay, epsilon bar, multiplied by dn, what is that? That is the energy of all these photons, of this many photons, passing through this cross-section area over a time interval of dt. And if I divide by dt, what do I get? I get the total energy emitted per unit time, don't I? And if I then divide this by area A, what do I get? I got the total power emitted per unit area of the black body. And that, by definition, is the total, is the power P. Okay, let's see what that is equal to. So we just plug in the expression for dn into here, which is 1/4 NaC dt, and cross out a dt, and I got 1/4 C, and then n times average energy. This is the average energy of all the photons. It doesn't limit ourselves, we're not limiting ourselves to a certain frequency, okay, all the photons. And n is the number of photons per unit volume, so if you multiply these two together, what do you get? You get a total amount of energy of all these photons per unit volume, and that by definition is U, the energy density, right? Big U over V, remember? So this is how you relate the radiation power and the energy density within. There is a 1/4 U times C. This is the total power radiated. But what about the power radiated per unit wavelengths, which is eventually what we're looking for? So I have to differentiate P with respect to lambda. So let's do that. I lambda equals dP over d lambda. P is 1/4 of C times U, so 1/4 C comes out, du d lambda. Now we already know what du d lambda is. In fact, we did that before. That's capital U, which means it's the energy density small u times V. So for d small u over d lambda, all we have to do is get rid of that V here. So we copy that into here, which is 8 pi hc. 8 pi hc divided by that, you see, without this V here. Lambda to the power 5. Lambda to the power 5. E to the power hc over lambda kt minus 1 right here. Okay. And just work out the combined term here, you finally arrive at this. I lambda equals 2 pi hc squared divided by lambda to the power 5 e to the power hc over lambda kt minus 1. This is the Planck's radiation formula in our textbook. There was no derivation in our textbook. They just stuff it down your throat. But here it is. We derived it. Can we use this Planck formula for black body radiation to explain all these experimental findings? The Stefan-Boltzmann law, the Wien's displacement law, and also correct the ultraviolet catastrophe. Of course, you bet we can do that, and let's see first of all how we can get the Wien's displacement law. So the Wien's displacement law basically tells you where the peak of that radiation power is. This is where di over d lambda equal to 0. This is how we find the maximum. And then I have to plug in the expression for I, which I derived 1 page ago. And this is what I have to do then. d lambda of this thing equal to 0. If you did that, you will find, unfortunately, you do not have an easy equation to solve. What you get is x to the power, if you finish this derivation, x times e to the power x divided by e to the power x equals minus 1 equals 0. And the x is defined as hc over lambda kt. This lambda is not just any lambda, it's maximum. This is the wavelengths corresponding to the strongest or maximum radiation. This equation has, it's not a conventional algebraic equation. We call it a transcendental equation in mathematics. It's a transcendental equation, and the only way we can solve it is by graphing it, so we can get an approximate numerical value. And if you did that, you'll find that x equals to 4.96511, so on and so forth. And from that x, which is hc over lambda kt, you can solve for lambda then. Lambda maximum, therefore, equals to hc over x over k, and then divided by t. So it's overall a constant divided by t. And that constant comes from x. That constant is equal to 2.89777, so on. And the unit is millimeter Kelvin. Okay, this is the Wien's displacement law. So the Wien's displacement law comes from the Planck's blackbody radiation, and we can plug in some common temperatures to find what kind of wavelengths do you expect to have the greatest radiation. That certainly depends on the temperature of the blackbody, or to be more precisely, this is the temperature at the surface of the blackbody. And if we plug in a specific temperature, if T equals to 5,800 Kelvin, I get lambda maximum equals to about 500 nanometers. What is the significance of 5,800 Kelvin? Well, that in fact, some of you may already recall, is the surface temperature of our sun. Okay, our sun is a good approximation to a black body. And the surface temperature of the sun is 5,800 Kelvin. Now, this is not the same as its interior temperature, which is actually several million degrees Kelvin, and that's where nuclear reaction takes place. This is only the surface temperature. At this temperature, the most prominent radiation coming from the sun is 500 nanometers. This is not only in the visible range, it is in fact yellow colored. This is why our sun looks yellow. And if you plug in T equals, say, 300 Kelvin. Now, what's the significance of that? That is the room temperature, right? And you will get a considerably longer wavelengths by a little more than 1 order of magnitude. In fact, the wavelengths is so long that we are going out of visible light range, so it's in fact infrared. This tells us that an object whose surface temperature is around 300 Kelvin or room temperature will radiate primarily in infrared. So you and I, and everything that we see, the wall, the table, whatever, they're all at room temperature and they do radiate. The primary radiation is in the infrared range, therefore we do not glow in the dark, right? Because our surface temperature is not high enough. And this also explains why your infrared remote control will never operate through the wall, because the wall not only radiates infrared, it also absorbs infrared because it's at room temperature, and therefore the infrared signal doesn't go through wall. If you want to use a remote control to control your video audio equipment from a different room, you have to avoid infrared frequency. You have to go lower to microwave frequency or radio frequency, then you actually be able to control that. Next, let's take a look at the Stefan-Boltzmann law. The Stefan-Boltzmann law is the total power emitted by the entire black body, not limited to a single frequency. So we have to integrate over all the frequencies up. And this is the Planck's formula for I. So we integrate over that. Let's tackle this integral. There is a common trick that physicists used when you deal with complicated integrals like that. And that is, we turn this integrand into a dimensionless quantity. So let's introduce a dimensionless quantity. This is a good candidate, hc over lambda kt. This whole thing is definitely dimensionless because it's on the shoulder of an exponential. So let's define hc over lambda kt. We call it x. So x is a dimensionless quantity. We differentiate that, then we get d lambda equals to hc over kt dx over x squared. You have a negative sign, but you can get rid of that by using the appropriate upper and lower limits, and you plug that x in, and d lambda equals this, and then replace lambda with x again. Take all the constants out, and here's what we get if you did that. You're going to get 8 pi hc squared, and then kt over hc to the power 4. That actually comes from here and there. And then you are left with a integral x to the power 3 e to the power x minus 1 dx. You wonder how we find this integral. But this is only technical, and it's not all that important, because after all, this is a dimensionless integral, okay? Dimensionless. This is very important. Which means no matter what it is, whether you can find it out or not, it's just a number, okay? It's just a number which will be added to 8 pi, whatever, just a number. What we learned is that whatever that number is, the way the power of radiation depends on temperature is T to the power 4. Okay? T to the power 4. This is the most prominent feature of the Stefan-Boltzmann law because it says the total power radiation is P to the power 4. In fact, we can apply it to our sun as well. The total energy, the total power radiated by the sun can be calculated from the Stefan-Boltzmann law. It in fact is indeed proportional to the surface temperature of the sun to the power 4, that temperature being 5,800 Kelvin. Well, of course, we also need to know the surface area of the sun and so on, but all that can be calculated, and the result, if you do your calculation yourself, you'll find that it actually agrees very well with our observation. Our observation is the power of the sun captured at the surface of the Earth, which is very far away from it. And this agrees with the total power calculated from the black body radiation. Now, to recover the entire expression for the Stefan-Boltzmann law, we need to finish this integral. And so let's see all these constants if they work out or not. This integral, if you want to calculate yourself, well, good luck. It's not easy to do. But I can tell you what to do. What you do is you expand 1 over e to the power x minus 1, this whole thing, 1 over e to the power minus 1 as infinite series. Multiply by x to the power 3, you still get an infinite series. And you have to sum up all these infinite series after integrating each term, and you will get a result of pi to the power 4 divided by 15 if you did that. You don't have to do it yourself, but just take my word for it. This integral even has a name. It's called the Bose-Einstein integral. Okay? And if you did plug that in, you'll find P equal to 8 pi pi to the power 5. Actually, 2 pi to the power 5. K to the power 4 divided by 15. H to the power 3, C to the power 2. All these values, pi, k, h, c, we have their precise numerical values. So from that, we can find it out, and that is the Stefan-Boltzmann constant sigma. And turns out sigma to be equal to, according to the textbook, 5.670 times 10 to the negative 8 watts per meter squared per Kelvin to the power 4. This is the Stefan-Boltzmann constant. So you see, this is really amazing. It tells us, using the sun as an example, the sun is a very large object, of course. But even for such a large object, the total amount of radiation or the power of emission of the sun is actually intricately related to the very small world, to this constant c, the Planck's constant for the very small world. So quantum mechanics is not just relevant to the atomic world, it is also relevant for large-scale phenomena. That's because whatever happens at large scale, the root is still within the behavior of atoms and molecules, and in general, the atomic world, which is governed by the quantum hypothesis. Finally, let's see whether the Planck formula can resolve the Rayleigh-Jeans ultraviolet catastrophe. Here is the new expression from Planck. The radiation intensity per unit wavelength goes like this. The Rayleigh-Jeans formula tells us something is wrong when the wavelength approaches zero, ultraviolet catastrophe, because this curve, this intensity curve goes all the way up to infinity, giving you an integral which is infinity. But the Planck formula, we can take a look what happens when lambda approaches zero. When lambda approaches zero, lambda to the power 5 approaches zero, but you have also a power function which did not exist in the, actually you had an exponential function which did not exist in classical physics. And as lambda approaches zero, you have e to the power infinity. E to the power infinity approaches infinity. So you have 0 times an infinity, and guess which one wins? Well, here you have an exponential function which approaches infinity exponentially. Here you have a power function which approaches 0. Of course, the exponential one wins. So therefore, overall, this denominator will reach infinity at lambda equal to 0, and therefore, you flip it over, I approaches 0, not infinity. So this is the Planck formula behavior. It goes down to 0. You have averted the ultraviolet catastrophe. So this is a complete success story, the first complete success story of the quantum hypothesis. As a matter of fact, we have introduced this important constant, the Planck constant, which is very small, and it tells us the quantization of energy with a gap of h times f. In classical physics, we know this gap does not exist because the electromagnetic radiation can have any energy it wants. As we learned in relativity before, if the speed of an object goes back down to very small value, everything should go back to Newtonian mechanics. Everything should go back to classical physics. The same thing should happen here, and that is, if we take away the quantization, then everything that we learned here will revert back to classical physics. And the quantization of energy means there is an energy gap of h times f. If this gap approaches 0, no quantization would exist, and as a result, you would have no quantum behavior. Everything should go back to classical physics. And for a fixed frequency, how do you make this gap go to 0? You take h equal to 0. So at h approaching 0, you go back to classical physics, okay? Just like when c approaches infinity, or v approaches the speed approaching value much less than c, then you should go back to from relativity to classical mechanics. As a matter of fact, you can easily see that when h approaches 0, then e to the power whatever is very close to e to the power 1, e to the power 0, or at least something very small, and then e to the power hc over lambda kt. I can approximate as 1 plus hc over lambda kt, as h becomes very small. Now you minus that 1 here, so that 1 is gone, and then you're left with I lambda approaching whatever constant, 1 over lambda to the power 4. Right? You have lambda to the power 5, and you divide it by lambda, and there is a kt here. This, in fact, is the Rayleigh-Jeans formula. In the past we used f, now we use lambda. It's really the same thing. And this is another example of what's called correspondence principle. Very important principle in physics, in fact, very important principle in all of science. And that is, when you write a new theory to expand the horizon of the old theory, to take the old theory to a region where it did not work before, the new theory is only correct when if you take all the parameters back to where the old theory is supposed to be valid, the new theory should agree with the old theory. This is the so-called correspondence principle, and we see it actually works here. So, once again, our first success story of the application of the quantum concept. We will continue to build more examples, more evidences of quantum hypothesis leading to the birth of the theory of quantum mechanics.